Perhaps the metaphysical question that's garnered the most interest in intellectual history concerns the existence of God. Arguments for and against the existence of a creator come of several types. What's interesting for us is that the laws of physics have been used, and with the progress of contemporary cosmology, continue to be used on both sides of the debate. It's easy to confuse the words cosmology, the scientific study of the origins of the universe, with cosmetology, the art of applying makeup. There's no deep reason behind this. On the other hand, consider the similarity between the words astronomy and astrology. These do have a relation going back to their origins. Now, in the days before television, there was little to do at night but to look up at the dark night sky and ponder the wonders that could be seen. The sky changes. The sun, the moon, the fixed stars rose and set each night predictably. On rare occasions, something unusual happens. Planets move for a period in the opposite direction of everything else in the sky. Comets appear. Shooting stars happen in bunches. Eclipses blot out the sun. These things happen at seemingly random times. Life's like that too. Things are always the way they are, except that every once in a while something unusual happens. Occasionally it was a good thing, sometimes not. Wars, disease, droughts, famine, they seem to happen randomly. Life is orderly until it isn't. The sky is orderly until it isn't. Maybe the two are connected. Of course, to be able to spot the irregularities, one would have to be very well acquainted with the regularities. And the only people who would have the means to do the painstakingly detailed observational work necessary would be those who are already financially and politically advantaged. And these people, let's be honest, generally don't have the intellectual powers to do the work themselves. So, with this wealth and political power, they provided the means for those who had the learning and intellectual power, thereby creating a symbiotic relationship between those who studied the sky and those who wanted accurate predictions about what would happen on Earth. Astronomy and astrology are twins, born of the same wealthy parents with the same intelligent nursemaids. Both sides of this arrangement saw the divine in the working of the heavens. God was not only the creator of the universe, but his presence was noticeable in the workings. That's why René Descartes caused an uproar when he proposed his mechanical philosophy. The physical universe is made entirely of matter, and matter interacts with matter according to fixed and rational laws of nature. This is the realm of science. Descartes thought that human logic is sufficient to do all the intellectual heavy lifting here. If we think clearly and reason deductively, we will derive all of the laws by which the material world operates. To Isaac Newton, this bifurcation was an abomination that removed God from the day-to-day working of the universe. Newton believed that God was active in the world. Indeed, Newton thought that gravity itself was God's presence in the universe. Newton was concerned that views like Descartes' could lead to deism. Theism, Newton's view, is that the creator God remains present in the working of the world. Deism, on the other hand, posits that an all-perfect creator would have constructed a perfect universe and therefore would not be needed in its orderly running. Like a clock, it would need to be wound and then could be left to run perfectly on its own. Deists hold that there is a creator God, but that God is absent from the universe after the creation. Contrary to Newton's intention, his own theory became the leading argument of deists and even atheists. What Newton did was to provide us with both a theory and the mathematical machinery necessary to work in physics without having to consider philosophical foundations. Physics before Newton reads like philosophy. Physics after Newton reads like mathematics. That difference allowed us to do physics in a way that accounted for the how without having to muck around with all the why. Now, some, like Baron d'Holbach, contended that the system of the universe that Newton gave us leads directly to the lack of any need for any sort of divinity at all. In his masterwork, the system of nature, Dolbach dismisses those philosophers who thought that God was necessary to explain the continual motion of the heavens by writing, "These philosophers, also notwithstanding, they saw above them an infinite number of globes that moved with great rapidity round a common center, still adhered to their favorite opinions, and never ceased to suppose some whimsical cause for these movements until the immortal Newton clearly demonstrated that it was the effect of the gravitation of these celestial bodies towards each other." Newton, the believer who thought that his system of the universe vindicated the existence of God, is being cited as having undermined the existence of God. Newton's physics was being used as the center of mass in the Enlightenment argument for atheism. The opposite line was taken by many philosophers, such as William Paley. In his book, Natural Theology, Paley contends that the complexity of the working of the universe is a mark of its design, advocating what philosophers call the teleological argument for the existence of God, or the argument from design. Paley argues that what we see when we look at the world is interrelated structures, and those entail intelligent creation. Now, if you were walking along a deserted island and came across a rock, you wouldn't infer anything from the discovery. A rock, so what? But if you then came across a watch, you could only think that there had been people here before you. Rocks could just happen, but the structured complexity of a watch requires a watchmaker, an intelligent designer who crafted the intricate working system with its many interdependent parts. Paley points to aspects of living beings and argues that the structure is much more complex than any watch. So, if there's an inference of intelligent design in the case of the timepiece, there must also be in the case of living beings. Life implies the existence of a creator God. Descartes, Newton, and Dolbach argue the case based on the progress of physics, but Paley turns to biology. This biological argument became less influential after the work of Charles Darwin. Evolutionary theory gave a purely materialistic account for the properties of different species. Paley's argument turns on the complex elements of anatomy of animals. That complexity could be seen after Darwin as the result of purely material circumstances. If we want to understand the eye or the wing, after Darwin, we could do so in a way that involved a narrative that only made use of survival pressures under selection processes given random mutations. The aspects of life that Paley relied on seem no longer to entail the sort of intelligent creation Paley inferred. So, by the end of the 19th century, the teleological argument for the existence of God fell out of favor. Late 20th century physics, however, brought the argument back to life. The Standard Model is our best account of the laws governing everything except gravitation. The general theory of relativity accounts for that. All these equations have constants within them. That is, terms that have to be included in the equations to make the units come out right. Now, physicist Robert Dicke pointed out in his article, Dirac's Cosmology and Mach's Principle, that we can arithmetically combine these constants to give rise to dimensionless numbers. That is, multiply and divide these constants in combinations that make all the units cancel out. Suppose one of these numbers is a velocity, something, say, like the speed of light. Speed is measured in meters per second. If another one of these numbers was a length, say the Planck length, it would be measured in meters. Divide the speed of light by the Planck length, and the meters cancel out, leaving a number whose only unit is per second. Now, if another of these numbers was a time, and you multiply this per second number by the time in seconds, the result is a number that's just a number, no units. Okay, shuffling the numbers around arithmetically like this is just a mathematical game at this point. But Dicke points out that when we do this, the resulting numbers have completely unexpected relations among themselves. Numbers that should have nothing to do with each other. Things like the age of the universe, the mass of the proton, and the gravitational constant, when properly multiplied and divided by each other, seem to be intricately related. That's weird. That is, It would be weird if it happened completely randomly. But is it completely random? Physicist Martin Rees has argued that it seems to be the result of what's come to be called the fine-tuning of the universe. If these constants were slightly different in numerical value, a bit larger or a bit smaller, the result would be a universe completely incapable of giving rise to life. If the strength of the gravitational force, for example, were just a little bit weaker than it is, given the strength of the electromagnetic force, stars like the sun wouldn't burn as hot, wouldn't create the heavier elements within them, and wouldn't explode as supernovae, which disperse these heavier elements throughout space. All of these processes are essential for the possibility of life, and all are contingent on the constants of our equations being just so. If either the strong or the weak nuclear force were a little bit different, life wouldn't be possible. If the weak force were a bit weaker, the universe would have burned up all of its hydrogen too early in its history to have life appear. If it were a little stronger than it is, again, stars wouldn't create the heavier elements in the amounts that would be needed to give rise to the physical context in which life could arise. Our universe seems to have found the very small sweet spot that allowed it to give rise to the conditions which allowed life to come into being. If you look at the range these constants could have taken, the fact that they just happen to have been in the range in which we, living beings, see them is uncanny. It's as if someone was very carefully tweaking the cosmic dials to make it come out just right in order to guarantee that there would be life in the universe. Richard Swinburne, emeritus professor from Oxford, argues that this is exactly what we should infer from the fine-tuning of the universe. Swinburne contends that the facts arising from contemporary physics, from particle physics to cosmology, show an interrelation and a sensitivity that cannot but resurrect the teleological argument. Maybe we can no longer use the biological facts that Paley relied on in his version of the argument from design, but we can now use the sort of physical facts that Dickey and Rees are giving us in a new, updated version. One with the same conclusion, that the intricacies of the universe implies the existence of an intelligent creator God. Consider the range of possible universes. That is, universes whose laws have each possible set of values for the fundamental constants. How many universes are we talking about? Huge number. Now, consider the possible universes that contain life. It's an infinitesimally small number. If you were to contend that our universe was the one that was randomly created, that is, from the set of all possible universes, you just reach in and pluck in any given one, what are the odds of it being a living universe? The odds are microscopic. But if you were to contend that it was not at all random, but the result of intelligent design, then it makes perfect sense. Hence, he argues, the fine-tuning of the universal constants for the possibility of life, which we see does exist, infers with a very high degree of certainty that there must have been a creator God. If there is a God, then you would expect a universe with life. If there wasn't a God, you'd expect that there wouldn't be a universe with life. There is life in the universe, and to get it, the universe had to be a very specific way. So, Swinburne argues, far from undermining the sort of proof for the existence of God that Newton held to be the case, physics once again provides it. The fine-tuning of the universe, he contends, should be taken as sufficient warrant for belief in the existence of a creator God. This, of course, is only one possible response to the alleged fine-tuning of the universe. The positing of a metaphysical cause of natural phenomena worries many physicists and philosophers. The hope is that we need not refer to a cause outside of nature to explain the workings of nature. As such, a second approach to the question of fine-tuning is to deny the notion of tuning at all. This approach takes two very different forms. We could call these the necessity and contingency approaches to denying design. The necessity approach to denying design looks at the history of physics and sees a process. That process, as we discussed in the last lecture, is one of unification. As physicists have gone on about their work, what's emerged step by step is a coherent, unified picture of the universe. If the future resembles the past, and there's every reason to think this is going to be the case, progress in physics will continue along this path. This process has started with a vast array of widely different sorts of phenomena and boiled it down to a small handful of laws and entities. This history has led to the current state, which has given us the Standard Model, a rather minimalist accounting of the basic components of the universe, and we have laws that, while we know they're not finished, pretty well account for most of what we see. Those laws have a certain form, and all include a few constants, at this time in the process, which need empirical determination. But as the process works on, these constants may turn out to be interdependent, thereby decreasing their number. Indeed, the number may even decrease to zero. The ultimate form of the laws of nature may themselves decrease to a single principle containing no underdetermined quantities. If this is the case, then the fine-tuning question goes away. The whole question was a result of our lack of knowledge about the actual laws of nature. The problem was a pseudo-problem. Now, maybe this is the case. Maybe it isn't. How would we know? The necessity approach does away with the need for supernatural interference, but it doesn't do away with faith, because the belief that the ultimate structure of the universe must be one certain way without having evidence in support of it, well, that's pretty much what's required here. The response is that this belief is different from the sort of faith needed for belief in the existence of a divine being, because it's the result of an inference from observable instances. In this case, the data is the flow of our best physical theories over time. We have a string of ever-improving theories that seem to be pointing in a direction. All we're doing is extrapolating from the data. Those on the other side point to the data presented in the argument for fine-tuning. They contend that they too are extrapolating in the same sort of way from empirical data. There are arguments for the existence of God that are purely rational, that is, that rely only on ideas, but then there are those based on observational data, and this seems to be one of them. If they can base an argument on this topic in one direction from incomplete evidence, why should we shut down one in the other direction in a similar foundation? The contingency approach to denying design takes a different line, arguing that there's not actually anything here that needs explaining. The necessity approach we just examined holds that at some point we'll realize that the facts we're trying to explain have to be as they are, and therefore that the ultimate laws of physics provide the explanation all by themselves. On the other hand, the contingency approach contends that things just are the way they are. But if that's the case, there's nothing to explain. But what about all the coincidence? What about the fact that any of these constants had been just slightly different? Life would have been impossible. It does seem awfully odd that things would be just so unless there was a reason why we would thread the needle to create one of the very few universes that could sustain life. If you select the universe at random, you wouldn't get one that allows life to come to be. Why did we get the universe that does? Elliot Sober is the Hans Reichenbach and William F. Vilas Research Professor at the University of Wisconsin, and more usually considered a philosopher of biology. But he weighs in on this question of fine-tuning arguments in the philosophy of physics. His argument doesn't make the move of the necessity approach. We don't need to assume anything about the ultimate forms of the laws of nature. Take them just as they are. Let's also grant that the universal laws could be of a different form and that the constants could be of a different value. We'll allow all of this to be contingent. That is, not necessary, could be otherwise, just happens to be what it is. But then, what explains that all of this lines up to allow for and sustain life, including intelligent life that can consider it? If all of this could have been otherwise, but turned out to be as it is, and how it is just happens to be highly improbable, then surely we need an explanation for the choice. Sober argues no. Just because something's highly improbable doesn't mean that it was designed. Improbable things accidentally happen all the time. The key is to look at them from the proper direction. Consider Roberta. Roberta has it tough. Money problems, job problems, personal problems. Life was not going well. But then, Roberta hit the lottery. With one stroke, she became fabulously wealthy, and with her newfound resources, many of her problems could be solved. What explains why, among the hundreds of thousands of people who played the lottery, that it was Roberta, of all people, who won? Let's suppose that it's a simple sort of lottery, where people buy all the tickets and one ticket's pulled at random. When they pull the ticket, the person who bought the ticket with that number will be the winner. Before the number is selected, there is no winner. Everyone is equally likely, or in the case of a lottery, equally unlikely, to win. Now, if they sold, say, 250,000 tickets, the odds of winning are 1 in 250,000. As such, it's more than unlikely that any given person will win. But, given that a ticket will be drawn, it's certain that someone will win. So, from one direction, it's entirely unremarkable that someone won the lottery. Of course, someone did. They picked a winner. From the other direction, it's incredibly remarkable that someone won the lottery. It was so incredibly, unbelievably unlikely that it would be Roberta who won, but she did. Sober is arguing that the fine-tuning argument makes the mistake of looking from the wrong direction. We're holding the winning lottery ticket. We're in a universe that supports life. Why? Why was it Roberta who won the lottery? Just was. There's no supernatural explanation for her ticket being the one picked. A ticket had to be picked. The constants and laws had to be some way. Why this way? Just how they are. Nothing to explain. But this approach leaves some feeling dissatisfied. When was the lottery drawn? And of all the tickets in the cosmic lottery, really? It just happened to be ours that got picked in a single drawing? Well, maybe it wasn't the only drawing. If you pick enough times, you're bound to win. Maybe the numbers got picked twice a week, Tuesday and Friday nights at 7. Cosmologists had been puzzled by a strange phenomena. The universe seemed to be geometrically flat and thermally harmonious in a way that shouldn't be the case if far-flung parts of the cosmos can't communicate with each other. The answer to both of these questions came from the cosmologist Alan Guth, when he proposed the idea of inflation. According to this account, not long after the Big Bang, the young universe underwent a short period of rapid expansion. Because the universe had been small before the expansion, the parts were close enough to be in communication, so equilibrium could be established. It would then be maintained after the expansion. Second, the expansion would smooth out the geometry because everything would get rapidly stretched. So if you have energy in a region and the region gets bigger, then the average energy in each little part decreases. The energy has to spread itself over more volume, so there's less per unit volume. This means that as the universe rapidly inflated, it also rapidly cooled. This cooling would have been crucial to the form of the laws of the universe. Before the inflation, when the universe was young, small, and hot, the forces of the universe may have been undifferentiated. There may have been only one force, but as the universe cooled, the different forces separated out from each other. Physicists call this symmetry breaking. What's interesting is that the way the symmetry breaks may be a function of accidental properties. It might not be a necessary result. This might mean that it was the uncertainty around the instant of inflation of our universe that set the laws in their particular form and the constants at their particular values for our universe. This has given rise to the idea that maybe this inflation occurs multiple times. Why should our universe be unique? Maybe ours is just one universe that started with a big bang and then inflated like a bubble. But maybe there are others that banged in and then puffed up. Maybe each universe is just a bubble in a giant cosmic bubble bath. Philosophers like John Leslie, an emeritus professor from the University of Guelph, sees this as a naturalistic alternative to the theological argument from design based on the fine-tuning of the universe. If reality gives itself multiple tries at forming universes, then what we see is a form of natural selection that's not unlike what we see in Darwin's biological form. Random mutations in organisms are usually fatal. Occasionally they're not. In these cases, once in a rare while, the accidental change is advantageous to the members of the species in their environmental context. In these rare events, the mutation propagates itself through the species and there's evolutionary development. If there are multiple bubble universes, each undergoing inflation under slightly different initial conditions, then there will be multiple universes with multiple laws and constant values. Most will fail to develop because the laws and constants don't allow matter to form. Or, if so, stars burn too quickly to allow for the development of life, or too slowly to produce and distribute the materials necessary for life. Perhaps they just collapse in on themselves. But if we buy enough cosmic lottery tickets, we would eventually find a winner. Enough tickets will be picked that a universe with the proper characteristics will accidentally be brought into being. Life may happen to be created in it. This life may morph and mutate until it becomes sentient and intelligent. Ultimately, perhaps, this life will understand the working of the universe that gave rise to it. This life will write it down to communicate it to others. Ultimately, this life may even create video lectures for the great courses in order to explain it to other instances of life. I just hope that in the next successful bubble universe, I'm a little taller with more hair. Is this the answer? It accounts for our best physical theories without having to make use of anything supernatural, but it does make use of universes beyond this universe. Multiverse theory, as it's called, seems to give us a way around having to invoke religion. But is it testable? Are there ways to show that universes with laws that have different forms, constants with different values, maybe even more dimensions or different forces? Well, that's not a philosophical question. That's a question for physicists. But the question that it answers is a question that physicists have taken from and are now giving back to the philosophers. Why are we here? What does it mean? Does the universe have a function? Was it created so that we could be? Physics began in classical times as philosophy. It diverged and took on an intellectual life of its own. But in finding the answers to the big questions, it's raised more questions. And those new questions bring physics back to philosophy. Who's to answer these questions? Should it be philosophers or physicists? The answer is and, not or. Philosophy without physics is naive. Physics without philosophy is shallow. Physics and philosophy. Now, that's a project worth considering.